Well, hello, welcome to this video. Today we're going to look at this problem. So we have P is a prime number where P is different than 2 or 5. Show that the period length of 1 over P divides into P minus 1. So first of all, let's look at the definition of a period length. Period length is essentially, when you look at the expansion of fractions, how many digits it takes until it repeats. The smallest number of digits until it repeats. So for example, we have 1 over 3, which is equal to its expansion 0.3333 and so on and so forth. So we can see that the thing repeating is the digit 3. The digit 3. And then the period length is how long it is. And because it's only one digit, then the period length of 1 over 3 is 1. And it's the digit 3 that's repeating, and we will mark that a 0.3 with a line above it, saying that 3 is the thing that's repeating constantly. If we maybe look at 1 over 11, that is equal to 0.090909 and so on. And we can see that the thing that is repeating here is 09, which is 2 digits, so we have 09, 09, and 09 forever, which is 2 digits, so the period length of 1 over 11 is 2. And we mark that as 0.09 with the line above the entire thing, indicating that 09 is the thing repeating. So that's pretty much it for a period length. Now let's get on with the problem. Okay, now let's get on to the problem. So it seems kind of tricky how you prove that the period length divides into P minus 1. But actually that just means that P minus 1 digits actually repeat. So let's now actually go ahead and prove that. So we will mark N as the period length, and then P minus 1 as kind of a sub-period length. And by that I mean that P minus 1 is not the smallest amount of digits that repeat, but it is an amount of digits that do repeat. So for example, with 1 over 3, it's true that the period length is 1, but you can also say that you have 3 repeating. That's it, because 3 and so on and so forth. It's also 1 over 3. So that's what I mean by sub-period length. Now we're going to show that this implies that we have N divides into P minus 1. Which means that we just have to prove that P minus 1 digits repeat, which will tell us that the period length divides into P minus 1. Okay, so we're going to establish two things. One, if alpha is a natural number, then we have alpha times n digits do repeat. Repeat. And actually, it's pretty easy to see that. So I will be proving that, and it's going to be like homework for you watching. So we'll just mark that as done. But what we will prove is that if alpha is not a natural number, then we definitely have that alpha times n digits. If alpha times n happens to be a natural number, then that amount of digits don't repeat. So, let's see. So, here's what we're going to do. Because alpha is not a natural number, and of course I'm talking where alpha is positive, then we have that the fractional part of alpha is in the closed range from 0 to 1. And normally for a fractional part, the 0, it will include 0. But if it includes 0, then alpha will be a natural number, and it's not, so we don't include 0 here. So, now, let's see. So we'll look at alpha times n digits. We can say that alpha times n, we can split alpha into its whole part, which is its floor, and its fractional part, which are those kind of brackets around it. So we have this is n times the floor of alpha plus n times the fractional part of alpha. But then we'll incorrectly assume that this does repeat, meaning that this entire thing repeats, and then we have n times the floor of alpha does repeat. And why is that? Because the floor of alpha is a natural number, and we showed that if a number is a natural number, then it times the period length, amount of digits, does repeat. So this repeats, the entire thing repeats, but then that will mean that this also repeats. But now, alpha is in the range between 0 and 1, meaning that alpha, the fractional part of alpha, is smaller than 1, meaning that we have the fractional part of alpha times n is smaller than n. And here's our contradiction. We have an amount of digits, if this happens to be a natural number, smaller than n, which repeats. But we defined n as the period length, which is the smallest number of digits that repeat. And so there can't be any amount smaller than that. So we have our contradiction, and we've shown that this is correct. Okay, now that we've shown that if alpha is not a natural number, then alpha times n digits don't repeat if this is a natural number, we can say that the opposite of the opposite is correct. And by that I mean we reverse the direction of the arrow, but also reverse the sentences. So this means we have that this means that we have this following statement. If alpha times n digits repeat, which is the opposite of them not repeating, then alpha is a natural number, which is the opposite of this. Okay, now let's define some things. Let's define x in such a way that when multiplied by n, it will result in p minus 1. But we still don't know if x is a natural number, so we can't just say that n divides into p minus 1. But now, we know that p minus 1 didn't repeat, so x times n digits repeat. That's just for our assumption. But now, we know that by this, we know that this means that we have x being a natural number. But what that means is we can solve the equation for x here and get that p minus 1 over n is equal to x and is a natural number. And this means that n divides into p minus 1. Okay, we've shown that all we need to prove is that p minus 1 digits do repeat. Now let's do that. So let's look at, say, at a fraction which has p minus 1 digits repeating, and see if we can build anything off of that. So we will assume that the fraction is smaller than 1 because the whole part doesn't matter. We're just worried about what's after the dot. So we will have 0.a1, a2, a3, and so on until ap minus 1, when all of these a's are digits. But then, this means that we again have a1, a2, a3, and so on until ap minus 1, because this amount of digits repeats. And this continues on forever. This will repeat for the third time, fourth time, and so on. Now what we will do is you can say, take out an a1, a2, a3, and so on until an ap minus 1 out of this. So we'll have this a1, a2, a3, and so on until ap minus 1. And just to clarify, I'm not multiplying these are just digits of a number with p minus 1 digits. So this will be times what we have left, 0.00, then a bunch of zeros, till we have a 1. But the amount of digits here will be p minus 1. And I'll let you see why that's true. It's not that hard to see. And then we have another 0, 0, 0, and so on until another 1. And all of these are another p minus 1 digits. And this will continue on forever. So, what we can do, first of all, I'll number this p minus 1 digit number as k, where k will have to be a natural number. So, let's see. We'll have k times, now, this is what I'll write in the brackets. 10 to the negative p minus 1 plus 10 to the negative 2 p minus 1 plus 10 to the negative 3 p minus 1, and so on and so forth. So I'll let you think about why that's true, but it's pretty easy to see. It's not that hard. Now we can see that this is an infinite geometric series with the a being 10 to the negative p minus 1 and our r also being 10 to the negative p minus 1, because the power each time it can say decreases by p minus 1. And by the formula of a over 1 minus r, we get 10 to the negative p minus 1 over 1 minus 10 to the negative p minus 1, this entire thing times k, which we can simplify into k divided by 10 to the p minus 1 minus 1. And just by multiplying by 10 to the p minus 1 on the top and bottom on this fraction. Now, if we can somehow show that with k being a natural number, this can equal 1 over p, then we're basically done. We've shown that a number with p minus 1 digits repeating can equal to 1 over p, and does equal. It does equal to 1 over p by just, yeah. Okay. Now, let's look at the expression 10 to the p minus 1 minus 1. To me personally, it reminds me of Fermat's little theorem, which states that, let me write it up here, for every p prime number and a being a natural number, where p does not divide into a, we have that a to the p minus 1 is congruent to 1 mod p. Or I can subtract 1 for both sides and say that p divides into a to the p minus 1 minus 1. As long that p does not divide into a, and p is a prime and is a natural number and all that. But now, let's see. We know that p is not equal to 2 or to 5. And because those are the only prime numbers that divide into 10, we can safely say that p does not divide into 10. But then, by Fermat's little theorem here, we can say that 10 to the p minus 1 is congruent to 0 mod p, is divisible by p. Meaning that there is, let's say, a natural number r such that when you multiply by p, you get 10 to the p minus 1 when r is a natural number. Okay, now let's see. we can say that that means just by dividing by p and 10 to the p minus 1 minus 1, we have r over 10 to the p minus 1 minus 1 is equal to 1 over p. But now notice, if our r happens to be equal to k, then this entire fraction is equal to 1 over p, just like we want to prove. And we can be very sure that r definitely can equal to k, because I'll let you think about why that's true, but r cannot have more than p minus 1 digits, and we know that k can have at most p minus 1 digits too, and because this a1, a2, and so on can be zeros. Okay, now we can say that if r is equal to k, and it can equal to k, then p minus 1 digits repeat in 1 over p, an expansion of 1 over p. And like I said earlier, verbally, we know that r can equal to k. And a hint to why r cannot have more than p minus 1 digits is by looking at this. Okay, now that we know that if this can be true, then we can just set k equal to the appropriate r, such that we'll multiply by p will give us 10 to the p minus 1 minus 1. And we know that it will work super nicely with our fraction, meaning that our proof is basically done. So, if you want more content like this, please subscribe to my channel. I'll be uploading more problems like this in the future. And finally, that's it.